Looking at the whole ecosystem on the right, as we move towards a circular supply chain, the different groups within these buckets really become interrelated. So as we have in the bottom right, the lithium-ion battery recycling and primary battery metals. So taking different types of resources from the field that are lithium or nickel or cobalt bearing and developing different mechanisms and techniques for how to liberate those elements, how to purify them to battery grade, and how to sell them into the market. And then both the battery recycling and the primary metals can make identical materials made to the same specifications, and both can be done domestically in the US if done correctly. Those are sold up to the cathode and chemical refiners and waste material coming back into the recycling facility, and then the same with cell manufacturers and vehicle OEMs. So having relationships with companies in each of those other three groups becomes very important, as this is a bidirectional set of interactions. And it's important to note that recycling and primary metals are really independent in how they address these challenges. Battery recycling can be very quick to market, relatively quick to put up facilities, very short processing times, and returning essentially every material needed to make a brand new battery if done correctly. But for the next few years, the throughput will be somewhat limited by the amount of material coming back from the market. So there is scrap and defects made during manufacturing, there's end-of-life vehicle cells, end-of-life consumer electronics and stationary storage, but there still is a cap on that until larger amounts of material comes back from the field. Primary metals are the exact reverse. So many years to bring a new resource to market, to develop new refining and manufacturing techniques, but then once established, extremely large scale can be implemented and brought to bear within the US. So we intentionally are pursuing both of these strategies, which really complement each other on a timeline basis and the ability to address each of these global challenges. So we recently brought on a new board of directors, really working with the automotive OEMs to make sure we understand our customers well and who have large amounts of experience in this field. Beth was the general counsel of General Motors for many years, really led their ESG and sustainability group in-house, has given great insights. Sharif was the vice president of electrification at Ford for many years, also worked at Magna and Uber, and Julie and Rick each bring great experience to them. So having this well-rounded board really advising and providing governance has really accelerated our work over the past year. My background and much of the rest of the team we've brought on is, we were part of the initial design team for the Tesla Gigafactory outside of Reno. So many of us started back in early 2015, before we even broke ground on the factory itself. And we designed the physical building, the cell manufacturing layouts, the utility systems, and worked through the commissioning and really the defect reduction for that whole facility. And really seeing how we moved material from powders to slurries to coated electrodes to cells to modules to packs all under one roof, seeing the types of failures and defects that were generated on site. We had a very difficult time in the early days finding anybody who could actually take our defect and waste material and recycle it responsibly, especially within the US, and especially in a mechanism that was low environmental impact. And really seeing the amount of waste pile up and the void in the market and the lack of ability for companies to really handle that material, to recover the elements and to return it to market was very apparent back in the day. And then my third and fourth years at Tesla, I formed my own team in the R&D division that we called the Battery Material Processing Group, really working with unconventional resources that the traditional mining industry had determined was not economical to extract elements from those materials. So working with these unconventional materials, we formed our own wet chemistry laboratory, built our own R&D team, and started receiving dry sacks and drums and barrels of all different types of material from throughout the world that were lithium and nickel and cobalt bearing. Developing new ways to liberate those materials, new ways to refine and purify them into battery grade, and then very different mechanisms of how we would actually synthesize active cathode material from those recycled and unconventional virgin materials, and really uniting that part of the supply chain that unfortunately is still rather segmented with silos in between primary metal manufacturers and recyclers and cathode refiners and cell manufacturers. And really tying together those two different pieces the fundamental understanding of how to manufacture cells and modules and packs, and then understanding how to liberate elements from unconventional resources is really what led us to develop the two halves of our integrated battery recycling system. So my team and I developed this over the past 3 years, and really what we came up with is quite a bit different than the conventional methods, which really exist of smelting-based processes where whole batteries are dropped into a high-temperature furnace and they really follow the path of a conventional ore, or just a simplified process where batteries are dropped in an inert environment and shredded into a slurry, and then a complex set of processes are used to liberate one element at a time. So those processes each have many pros and cons to them. The thermal process really is rather polluting. Many people think that just because something is recycled, that has low environmental impact, and that's not always true. And the same with mining. Mining is not inherently high environmental impact. You really have to take one step further and actually look at the processes themselves. So what we've done is taken many of the techniques we developed for manufacturing cells and modules and packs, and we've developed a way to essentially run them in reverse order. So we can demanufacture in an automated fashion down to modules, selectively modules down to cells, dissect cells, and separate out the subcomponents all in an automated fashion without any direct labor. And by separating all of the support material early on, we're able to generate many types of byproducts to sell, but they also remove what would be contaminants down the road in the chemical extraction train. Because when you're trying to make cathode-grade metals, the biggest impurities are essentially the competing transition metals, having the aluminum, the iron, the nickel, the copper, and those is really the worst thing that you want to have. So demanufacture them up front really purifies and streamlines the material, and then allows in our chemical extraction train to have a much more targeted system. So on a very simple basis, it really consists of these two loops which operate in series with each other. However, there's quite a bit of feedback in between the two. Right when you start opening a cell, lithium specifically is intentionally a very mobile ion within the battery. It really exists in every single component. And once you open that casing up, it really disperses. And some companies are trying to do essentially separated processes where you disassemble or pre-process in one location and then extract the elements in a different one. And when you do that, you really lose a lot of the ability to access the free lithium that comes out once you open the cell. It usually comes out in a very dilute fashion. It usually is in some of the water and rinse water streams. And if you don't have the processes connected, it's hard to get especially high lithium recovery rates. So we have large amounts of feedback of early streams from our demanufacturing train going to secondary recovery in our chemical extraction train, and the reverse, where we can take some of the products from our train and put it back in the demanufacturing side. So it really is an integrated system on purpose. That's why we're able to get such high recovery of the transition metals and especially of lithium. And you notice both loops are water-based, and both have their own internal water treatment systems that really allow the water itself to work in a closed loop, and also the counter ions to the chemical agents. You are generally just interested in one of the counter ions when you're doing pH adjustments and selective extractions, and the counter ion then becomes a waste in typical processes. But we intentionally regenerate those streams in both of our loops here to recover not just the water, but also each of the acid and caustic agents that are used throughout the process. It makes a very large difference on the environmental impact of the train and also on the economics. Because in conventional systems, the largest OpEx by far is the chemical consumables in the chemical extraction train, the acids, the bases, the solvents. So because of these different designs where we have the automated demanufacturing up front and then the much more targeted chemical extraction in the back, we're able to make significant improvements on specific CapEx and specific OpEx compared to baseline facilities. And then as mentioned, because of the dramatically lowered chemical consumables, it makes a large difference on the environmental footprint for the entire life cycle of this process. So we're fortunate enough to have won a few corporate awards. A few years ago, BASF hosted a competition looking for the most promising lithium-ion battery recycling technology in the world. They ended up choosing us as the only winner of that competition. And in the US, as we know, there's very little active cathode manufacturing. The only two real scale facilities are both operated by BASF in the Midwest. So having them through this relationship is very important as a strategic and a potential customer of the battery cathode grade products that we're selling here. Separately last year, we also won a different award from the US Advanced Battery Consortium. So working with General Motors, Ford, Stellantis, and Department of Energy, where they really said, we don't want to just see a recycling operation. We want to see the entire life cycle demonstrated at once. So we proposed recycling entire full-scale battery packs, recovering the elements, purifying them, actually synthesizing new high-energy density active cathode material, and actually fabricating full-scale automotive battery cells, and then testing those cells against identical ones made from virgin, non-recycled material. So we're going through that project right now, partnering with BASF and with C4V, a cell manufacturing company in Western New York State. So again, of the 4 sectors that make up this closed-loop supply chain, representatives from every sector are included in this one project. And this is not just bench-level analytical samples. This is hundreds of kilograms of material and full-size automotive cells, demonstrating that recycling is not just a token technology, but can actually contribute, and not just in a blended fashion, but having 100% recycled active metals in a full-scale battery cell. So much of the work we've done sending analytical level samples to prospective customers, to cathode manufacturers, to cell and vehicle manufacturers. And being on the other side of the table for many years, we always understand that these are not commodity metals, these are specialty chemicals. Every customer has a slightly different specification. They want a little different type of material based on the specific processes they use. So the first thing we did was work with our prospective customers to co-develop specs for every single impurity, for every single type of morphology, actually agreeing on the specifications they wanted. And they're used to buying products from ore, from virgin metal, where no matter what type of resource you have, to some degree, essentially, the entire periodic table is in a material sample when you pull it up. So there's so many different types of impurities they had to worry about. We see it was much more of a wide breadth, really trying to reduce large amounts of impurities. Whereas when you start off with a recycled material, the type of unique species in a battery is much smaller than a virgin material. So we're able to be much more targeted, and speaking with them, we're able to surpass the level of impurity removal by an order of magnitude compared to what you generally make from a lot of the virgin materials. So there's been a lot of back and forth about seeing the impact that has on the type of active cathode they make and the performance it results with in the cell itself. So we're currently building our first pre-commercial facility. This is just outside of Reno, Nevada. This will process just over 20,000 metric tons per year of batteries, about 5 gigawatt hours per year on an energy basis. And again, much of our team is from the early Gigafactory design team, so we did it the traditional way, where we bought a greenfield site, we designed the building itself from the ground up, we've designed our own utility systems, and essentially designed the building around our own process. So we just finished construction of the building and the site, and we're now moving forward with the installation and commissioning of our commercial scale equipment. So over the next few months, we'll be going through the commissioning process and then ramping the throughput throughout next year. So it was some exciting times the past few months. During the supply chain issues, there are a lot of fun to deal with securing materials. We did some midnight concrete pours. There's a cool picture on the right of it, just during sunset, or sunrise actually, some of our pad being poured, and really pulling this facility together. This is the first 30,000 square feet of the building that is now equipment ready for move-in. And as mentioned, separate from recycling, the people who've spoken earlier today really talk about the magnitude of the need for these battery metals. The unprecedented construction of electric vehicle factories, of cell manufacturing facilities, and it's not being followed up the pipeline by active material refining and specifically by battery material manufacturing. So while battery recycling can help, we really need to have much larger scale projects online to help address these problems. And that's why we also have our primary metals manufacturing division. So about 2 years ago, we were evaluating many different types of unconventional lithium-bearing resources. We started working specifically with a resource found in central Nevada. So it's a sedimentary claystone resource that really hasn't ever had commercial scale production of lithium from it. It's very different from hard rocks. It's very different from brines, which are the conventional pathways. And because of that, people tended to ignore it because it really wasn't one of the conventional resources. And if you just try to apply a conventional process flow sheet for how you extract lithium from hard rock or from brine, it doesn't work especially well from these types of sedimentary resources. So instead, we started from first principles and developed our own custom process flow sheet for how to liberate lithium from this very unique type of resource, how to purify it, and how to convert it into a battery-grade lithium hydroxide. We did it at the bench scale over the past 2 years. We ended up buying almost 11,000 acres of land leases in central Nevada, and we've been both quantifying the resource itself in Nevada and developing our own process flow sheet for how this metallurgy will actually work to make this battery-grade lithium hydroxide product domestically. And while you look at the US, it's true that lithium isn't especially rare. You know, on a metal basis, globally, we made just over 100,000 metric tons last year. Just in the US, there's over 9 million tons of proven reserves. But when you look at the locations that are of interest, they tend to be hard rocks down in North Carolina, different types of brine projects in Arkansas and Louisiana, the high temp geothermal resource in Salton Sea, and then Utah has its own brine resource in the Salt Lake. And then the only functioning mine in the US is a very small one, a brine facility in southwestern Nevada. So it looks like there's large amounts of material, but unfortunately each of these locations is having some severe challenges in moving up. So there haven't been operating mines in North Carolina for decades. They're facing large amounts of pushback to getting those re-permitted. In Utah, they're having a once-in-a-century brine, or a drought, that's been lasting for many years. So having an evaporation-based mineral extraction process in the middle of a century-long drought is a very difficult proposition. And California has gone ahead and passed a lithium tax, even though there are no lithium facilities in California yet. So it's a preemptive tax for any facility that will eventually be built there, almost discouraging production in the state. So while there are several options, when you look at the attractive ones, it really does make Nevada-based resources stand out. Just about 40% of all of known lithium resources in the US are in Nevada itself. It's a very mineral mining friendly state, and it is the very high potential region going forward. So like I mentioned, we have our own claim set here, just outside the town of Tonopah, Nevada. A lot of these mining locations, you usually find a resource in the middle of nowhere, and you've got to clear a forest to make a road to access it, to run high voltage power lines to it, to get water infrastructure to it. We happen to be at the intersection of two of the biggest highways in the state. We have a 120,000 volt transmission line directly through our property, and we're directly by the town of Tonopah, which is a long history of gold and silver mining, and the town is actually encouraging us to build a facility there. So a lot of these tailwinds are in alignment about bringing this new type of process online to identify this resource. And then when it comes to the extraction process itself, our bench work we performed over the past 2 years, we started working with DuPont to manufacture some custom components and media for us. And then last year we applied to some US Department of Energy funding, essentially saying we want to take this bench scale data and now build a multi-ton per day field demonstration unit. And after much due diligence, we were able to win that grant last year. And last fall, we kicked off the project, now building our multi-ton per day demonstration scale system. So DuPont is our co-applicant in this project. And as we scale up from bench to multi-ton per day field, as far as the metallurgy side, and we also scale up the quantification and development of our resource, this is an operation that has real possibility to be addressing the domestic lithium shortfall over the coming years. So still many more steps to go. And again, the recycling system is very quick to market, over the next few months, which works very complementary for how we now scale up this primary lithium system. And each system makes the same products. We make the same lithium hydroxide to the same specification that to our customers is chemically indistinguishable. So as we ramp up our recycling facility, it will be this first pre-commercial unit and then much larger commercial scale facilities afterwards, really driving a lot of the high throughput as we ramp up our primary system in parallel. So just in conclusion, we really think having these two strategies together is necessary for the country. We can't choose one or the other, and there really are large amounts of synergies between developing them both. The types of skill sets of our employees, the types of facilities we have, even a lot of the back-end purification and conversion processes are near identical. So we're excited to scale up both of these units and to help to start addressing a lot of the challenges you each laid out this morning. So thank you.